You measure one tablet from a factory line. It is a bit heavy. You measure another. It is a bit light. Then another. Then another. Each tablet has its own small mess. Powder packs unevenly. Air shifts. Machines vibrate. Scales wobble. Workers adjust settings. None of that looks neat on its own. But then you average many tablets at once. Now something strange happens. The averages stop looking jagged. They start to pile up in a smooth hump. A bell shape appears. It appears again and again, even when the raw pieces did not look like a bell at all. That is the puzzle. Why should many rough causes added together produce one clean shape? The central limit theorem gives the answer. It says that if you add many independent random pushes, then center and scale the total in the right way, the result tends toward a standard bell curve, n of 0, 1. This is not just a math trick. It is the working reason we can turn noisy data into stable judgments. This theorem built the practical world of margins of error, lab trial summaries, factory control charts, quality sampling, routine confidence intervals, and much of modern survey work. It also shaped astronomy in the 1800s, industrial statistics in the 1900s, and everyday data analysis for governments, hospitals, and firms. If you want to know why averages calm down, this is the equation. In daily life, single observations are wild. One voter answers a poll after a bad commute. One patient has an odd reaction. One die roll lands on 6. One tablet comes off the line a bit too heavy. A single draw tells you little. Yet whole fields act as if averages are trustworthy. Pollsters report support rates. Drug trials report mean effects. Factories monitor average fill weight. Websites compare average click rates. Investors talk about average returns. Why do they trust those averages at all? The central limit theorem sits under that trust. But before it became a theorem, it was a practical headache. In 1733, Abraham de Moivre worked on games of chance. He wanted a fast way to estimate binomial probabilities. If you toss a fair coin many times, what is the chance of getting near half heads? The exact count gets painful when the number of tosses grows. De Moivre found that the binomial pattern near its center could be approximated by a smooth bell-shaped curve. This was an early root of the central limit theorem. It was not yet the full result used now, but it was a major step. A few decades later, Pierre-Simon Laplace pushed the idea further. By 1810 to 1812, he linked these approximations to broader problems. He cared about errors in measurement, astronomy, and inference from large counts. In his hands, the idea moved beyond gambling tables. Then, the story changed again around 1900. Alexander Lyapunov gave a more rigorous general theorem. He showed conditions under which sums of independent random variables approach the normal law. In the 1920s and 1930s, Jarl Waldemar Lindeberg and William Feller sharpened those conditions. They helped shape the modern form. This was not one flash. It was a long repair job. A theorem now taught in week 1 of statistics began with a gambler's counting problem. The real problem was plain. The raw world is not normal. Coins are not bell-shaped. They are 2-point outcomes. Dice are flat over 6 faces. Defects come in lumps. Purchase amounts lean to one side. Errors can be clipped, rounded, or one-sided. Human answers can bunch at 0, 5, and 10. So why do averages so often look normal? That question has 2 parts. First, what happens when you add many independent random variables? Second, how should you scale that sum so different sample sizes can be compared? Without scaling, the total spread grows as you add more terms. A sum of 100 noisy values is wider than a sum of 4. You need 1 yardstick. The theorem says to subtract the expected total, then divide by the right spread. Then the shape settles down to a standard normal bell. That is the deep claim. It is not about one coin or one die. It is about the shape that emerges from many small pushes. Before good approximations, people often did one of 3 things. They computed exact probabilities, if the case was simple enough. This works for small binomial tables. It fails fast when the numbers get large. Or, they used rough rules of thumb. They would say a result looked unusual, or close to expected. But they had no clear measure of how unusual. Or they leaned on special cases. If the source was already normal, then some stayed normal. But that did not solve the bigger problem. Most real sources are not normal. Astronomers needed error estimates. Insurance offices and state officials needed summaries of counts. Later, factories needed rules for production variation. Exact formulas were too narrow, rules of thumb were too loose. A wider principle was missing. This mattered because decisions cost money, health, and trust. A factory has to know whether its process is drifting. A trial has to know whether a mean difference is likely real. A poll has to know how much random wobble to expect. A business test has to know if version B beat version A. A bank has to know what averaging really buys in a portfolio. In each case, the same need appears. People need a stable way to summarize noisy data from many sources. The central limit theorem does not tell you everything, but it tells you why averages often become manageable. That is enough to build methods around them. The bell curve often appears not because nature loves bells, but because aggregation smooths rough edges. The gap was clear by the 1800s. It was urgent by the 1900s. People had examples where bell-like behavior appeared. They had de Moivre's binomial approximation. They had Laplace's broader use in error theory. But they did not yet have a clean, general answer to the puzzle. What exact conditions are enough? How much independence do you need? How much finite spread do you need? What if one term dominates the rest? What if the tails are too heavy? Those questions lead us to the cast. They lead to the people who turned a useful pattern into a theorem with limits. Start with Abraham de Moivre. He was a Huguenot refugee in England. He made his living with math. He was good at probability. A lot of that work came from gambling tables. In 1733, he wrote a short Latin pamphlet. Its title was Approximatio ad summum terminorum binomii. He showed that the middle terms of the binomial expansion could be tracked by a curve we now call normal. That gave people a shortcut for large coin toss problems. De Moivre did not hand us the modern theorem, but he saw the bell shape rise out of repeated yes-no trials. That mattered. Then came Pierre-Simon Laplace. Laplace aimed wider. He pulled probability out of games. He pushed it into science and state work. Around 1810, and then in 1812 in Théorie analytique des probabilités, he widened the normal approximation. He tied it to measurement error, he tied it to statistical reasoning. For Laplace, probability was a language for uncertain knowledge. He changed the question. The old question was how to price or estimate a gambling table. The new question was how repeated random effects combine in the real world. Then came Alexander Lyapunov. By 1900 and 1901, probability needed rigor. Mathematicians wanted exact conditions. They did not want good stories alone. Lyapunov gave one major route. He set conditions on independent variables that make a normalized sum move toward the normal law. He used transforms. That made the argument precise. Then came J.W. Lindeberg and William Feller. In 1922, Lindeberg gave a condition with a sharp idea. No single term should hijack the sum. In 1935, Feller made the modern form clearer. He also clarified how the conditions fit together. Together, they gave the version students and researchers still point to when they ask a hard question. When does the central limit theorem apply? One more name belongs here. George Polya. In 1920, he used the phrase central limit theorem. The name stuck. But this cast is not just mathematicians. It also includes the people who used the idea. Astronomers used it to handle measurement error. Statisticians used it to justify inference from sample means. Industrial engineers used it in quality control. Pollsters used it to report margins of error. Medical researchers used it to compare treatment groups. The theorem became famous because it met a need in many trades. The same theorem that helped with coin tosses also helped weigh tablets and judge star positions. To see why, we need the equation itself. We need every part of it. The formula is this. Z sub n equals open parenthesis sum over I of x sub I minus n times mu, close parenthesis, divided by open parenthesis sigma times square root of n, close parenthesis, tends to n of 0, 1. Here, Z sub n is the standardized total for n observations. Sum over I of x sub I is the added total of the observed random variables x sub I. X sub I is the ith random variable in the collection. N is the number of terms you add. Mu is the common mean, or average value, of each x sub I. N times mu is the expected value of the whole sum. Sigma is the common standard deviation of each x sub I. Square root of n is the square root of the number of terms. Sigma times square root of n is the standard deviation of the sum when terms are independent and share variance. Tends to means converges in distribution as n grows. N of 0, 1 is the standard normal distribution, with mean 0 and standard deviation 1. This formula says something exact. Take many independent random variables. Give them the same mean, mu. Give them the same standard deviation, sigma. Add them. Then subtract the total you expected to get, which is n times mu. Then divide by the natural spread of that total, which is sigma times square root of n. What you get is z sub n. As n gets large, z sub n moves toward the standard normal curve. The formula is about sums, but it is also about averages. If you divide the sum by n, you get the sample mean. You can then rewrite the same idea for that mean. After you center it by mu and scale it by sigma divided by square root of n, it also tends toward a normal shape. That is why the theorem is so useful. Most practical summaries are means, rates, and proportions. For a fair coin, de Moivre's 1733 approximation let people estimate large headcount probabilities with a bell curve. They no longer had to grind through the exact binomial expansion each time. Make it concrete with tablet weights. Suppose a factory fills tablets with a target of 500 milligrams. Each tablet weight moved for many small reasons: powder flow, moisture, press force, sensor noise. Let x sub I be the weight of tablet I. Let mu be 500 milligrams. Let sigma be 4 milligrams. If you weigh one tablet, the result can look odd. If you average 25 tablets, the average is steadier. If you average 100 tablets, it is steadier still. The theorem tells you why. Random highs and lows partly cancel. The average has a spread of sigma divided by square root of n. It does not keep the full spread sigma. So if n equals 100, the standard deviation of the average is 4 divided by 10. That is 0.4 milligrams. That is a big gain in precision. Notice the word precision, not truth, precision. The theorem tells you the random spread around the true mean. It does that if the sample was drawn well and the conditions fit. It does not promise the sample is fair. It does not promise the sample is complete. It does not promise the sample is free of bias. This is why people can trust average tablet weights, poll estimates, and trial means more than single observations. There is also a visual claim inside the formula. The source distribution can look strange. It can be skewed, it can be flat, it can be clumped. But once you add enough independent terms and standardize the result, the final shape often looks like a bell. The theorem does not say the raw data become normal, it says the normalized sum does. In practice, the bell curve often belongs to the average. It does not belong to the raw data. But why divide by square root of n? Why should many strange inputs blur into one stable shape? We are not doing a formal proof here. We are building the intuition that makes the formula feel hard to escape. Start with independent random variables, x sub 1 through x sub n. Each one has mean mu. Each one has standard deviation sigma. Now add them. S sub n equals x sub 1 plus x sub 2 plus ... plus x sub n. Here S sub n is the sum of the first n random variables. X sub 1 is the first random variable, x sub 2 is the second random variable, x sub n is the nth random variable. What is the mean of the sum? Means add. So the expected value of S sub n is n times mu. What is the variance of the sum? For independent variables, variance is add. Each variance is sigma squared. So the variance of S sub n is n times sigma squared. Then the standard deviation of the sum is square root of n times sigma squared. That is sigma times square root of n. That is the key scale. If sigma is 4 milligrams for one tablet, then the sum of 100 tablet weights has standard deviation 4 times square root of 100. That is 40 milligrams. The average has standard deviation 40 divided by 100. That is 0.4 milligrams. So when we standardize the sum, we subtract its mean, then we divide by its standard deviation. Z sub n equals open parenthesis S sub n minus n times mu, close parenthesis, divided by open parenthesis sigma times square root of n. Here, Z sub n is the standardized sum. S sub n is the raw sum of the n observations. N times mu is the expected value of that sum. Sigma times square root of n is the standard deviation of that sum under independence and common variance. Now Z sub n has mean 0. Now Z sub n has standard deviation 1. We have put totals from different sample sizes on one shared scale. That explains the denominator. It does not yet explain the bell. Why should the shape approach n of 0, 0, 1? Think of each x sub I as a small push. Some pushes go high, some go low. If the pushes are independent, their fine details matter less once many are combined. Sharp corners blur. Gaps fill. The total becomes the result of many small offsets. No one offset controls the whole picture. A die gives a good picture. One die roll is flat across 1 through 6. 2 dice already give a triangle-shaped sum. 10 dice give a smoother hump. 50 dice, once centered and scaled, look strikingly bell-shaped. The same thing can happen with skewed sources. But two conditions matter. No single term can dominate. At small n, the source shape still leaves marks. As n grows, those marks fade on the standardized scale. The spread of a sum grows like square root of n, not n. That one fact explains why averaging works. The total signal grows with n. The total noise scale grows with square root of n. So the noise in the average shrinks like 1 over square root of n. That is why bigger samples usually give tighter estimates. Not infinitely tight, not magically right, but tighter in a way you can measure. One historic route to proof uses characteristic functions. That is a transform method. It tracks how distributions combine when you add them. That route is elegant. It is also powerful. But the practical heart is simpler. Add many small independent effects. Center them. Scale them by their natural spread. A stable bell emerges. The theorem is strong because it does not care much about the exact source shape. It cares more about the buildup of many small effects under the right conditions. A jagged source can still feed a smooth average because addition acts like a blur. But this blur is not universal. There are hard limits. One famous failure shows them. The central limit theorem is strong. It is not a free pass. The first wall is sampling bias. In 1936, the Literary Digest ran a huge poll for the US presidential race. It gathered about 2.4 million responses. That was enormous, even by modern standards. The poll predicted that Alf Landon would beat Franklin Roosevelt. Roosevelt won in a landslide. What went wrong? The sample was biased. The magazine drew heavily from telephone users, automobile owners, subscribers, and similar lists. In 1936, those groups were more affluent than the full electorate. There was another problem. Response itself was selective. The poll was precise about the people who answered. It was not accurate about the nation. This is the cleanest warning tied to the theorem. The central limit theorem gives the shape of random error around the sample you actually drew. It does not fix a bad sampling frame. It does not erase non-response bias. It does not rescue tilted data. A biased poll with 2.4 million responses can be precise. It can still be wrong. That split between precision and accuracy matters everywhere. A bathroom scale can be off by 2 kilograms. It can still give the same wrong answer each time. A web experiment can randomize badly across users. It can still report tiny p-values. A factory can sample only the easy hours. It can then miss a night shift drift. A clinical registry can overstate outcomes if it overrepresents healthier patients. The theorem handles random fluctuation under stated conditions. It does not guarantee that those conditions hold. The second wall is heavy tails and infinite variance. Many financial returns look as if they can be averaged over calm periods. But some risk processes have tails so heavy that extreme events dominate. If the variance is not finite, the usual central limit theorem can fail. Then the sum may not settle into the standard normal law at the usual scale. One giant shock can overpower many small ones. That is why naive risk models can understate danger. If losses come from a fat-tailed process, more data does not always buy the normal approximation you hoped for. There are other walls. Dependence can break the simple story. If observations move together, variances do not just add in a clean way. Time series need care. Clustered data need care. Network effects need care. Small samples can also fool you. The theorem is asymptotic. It tells you what happens as n grows. For strongly skewed data, large enough may be much larger than you hoped. The original puzzle was why averages become bell-shaped, when the parts are not. The wall tells us this happens under conditions. It does not happen by magic. The theorem's most useful lesson may be what it cannot fix. So the real trade is not whether to use the theorem. It is how to use it without fooling yourself. The central limit theorem is a workhorse when you respect its conditions. It is a trap when you confuse precision with truth. Use it first for confidence intervals. If sample means are close to normal, you can judge how far an observed mean may sit from the true mean. That is the base of many standard intervals in medicine, public policy, and business reports. Use it for sample size planning. The standard error of the mean shrinks like 1 over the square root of n. Here, n is the number of observations. That lets you estimate how many observations you need to cut random noise in half. The answer is not double the sample. It is quadruple it. That is harsh. It is also useful. Use it for control charts in factories. Plants often track group averages, not single items. A single reading may lean or skew, but a group mean is often close enough to normal for day-to-day watch. That helps catch drift, before it turns into scrap, recalls, or waste. Use it for A and B tests. If you compare average outcomes across large random groups, the theorem helps justify a normal approximation for the gap in means or rates. That gives you standard errors, z-scores, and confidence intervals. It gives you a sober way to ask if a lift is real or just luck in the draw. Use it for portfolio averages too, but with care. Small risks can wash out when they are independent. That part is real. But if risks move together, or if losses have thick tails, the gain from diversification can be much weaker than the neat bell curve story suggests. The record is plain. Abraham de Moivre made large binomial sums usable in the 1730s. Pierre-Simon Laplace pushed the idea into astronomy and error work by 1812. Alexander Lyapunov gave clear conditions around 1900. Lindeberg and Feller shaped the modern theorem in the 1920s and 1930s. By the middle of the 20th century, this result had become a main beam in practical statistics, from polling to medicine to industry to economics. The theorem did not make people all-knowing. It gave them a strict way to separate random wobble from signal when they averaged many observations. That changed real work. Astronomers could sum repeated measures with clearer error bars. Factories could watch process means instead of staring at item-level noise. Clinical researchers could compare group averages with known uncertainty. Pollsters could put a number on sampling error, at least when the sample was built well. Textbook statistics could gather around one common limiting shape. Here's the reason the theorem works. The formula is z sub n equals the sum over I of x sub I minus n times mu divided by sigma times the square root of n, which tends to n of 0, 1. Here, z sub n is the standardized sum, x sub I is the ith observation, mu is the true mean of each observation, sigma is the true standard deviation of each observation, n of 0, 1 is the standard normal distribution with mean 0 and variance 1. That line tells the story in plain terms. Means add. Variances add. Standard deviation grows like square root of n. Once you center the sum and scale it, the fine details of each source start to wash out under aggregation, but only if the setup is sound. So use a checklist. Ask if the sample is biased. Ask if the observations are independent enough. Ask if the variance is finite. Ask if the tails are not wildly dominant. Ask if n is large enough for the shape you start with. Then use the theorem to estimate uncertainty around averages and totals. If those checks fail, switch tools. Use robust methods. Use resampling. Model the dependence. Use heavy tail models. Fix the sample design before you compute a margin of error. A clean formula cannot rescue a dirty sample. That is the trade. The theorem gives calm in the face of noise. It does not forgive bad data. The central limit theorem explains why averages become stable when single observations are messy. It works by centering a sum at n times mu and scaling it by sigma times square root of n, which reveals a bell-shaped limit, n of 0, 1. Use that power for random noise, not for bias, dependence, or fat tails, and the theorem becomes one of the most reliable tools